Welcome to Alpha C Learning, session 57. We are discussing oxidation of alcohols. In previous session, we learned few reagents, and in which few reagents are mild oxidizing agents. As we discussed that mild oxidizing agent doesn't mean weak oxidizing agent. And there are few reagents which do not disturb carbon-carbon multiple bonds like Jones reagent, Collins reagent, like that. And there are few reagents which disturbs or which oxidizes carbon-carbon multiple bonds like acidified potassium permanganate, alkaline potassium permanganate, acidified potassium dichromate. These reagents can oxidize carbon-carbon multiple bonds also along with OH groups. Not only OH groups means not only primary or secondary alcohols. Along with that, but also along with that, other oxidizable groups like carbon-carbon double bond and carbon-carbon triple bond gets oxidized. So we learn few reagents. Similar to that, there are few more reagents, and we are going to discuss mechanisms as I mentioned that in previous session. Chromic acid, how it undergoes how it acts as oxidizing agent. And in case of KMnO4 and osmium tetroxide, and they are involving in syn hydroxylation, but chromic acid is not going to take part in such type of oxidation, and how that mechanism proceeds, let us see in this session. And continuation to that one, manganese dioxide, which is selective oxidizing agent. Manganese dioxide is a selective oxidizing agent. It oxidizes allylic and benzylic alcohols just like Collins reagent oxidizes. Here this one also oxidizes. This one means MnO2 also selective oxidizing agent. It also oxidizes allylic and benzylic alcohols without disturbing that carbon-carbon double bonds and triple bond. Let us continue. Here I used to consider allyl alcohol. This allyl alcohol upon MnO2 acetone, allylic alcohol converts into aldehyde without disturbing carbon-carbon double bond. Similarly, benzyl alcohol, this benzyl alcohol secondary and benzylic alcohol upon oxidation, we are getting phenyl methyl ketone, but not this carbon gets oxidized. And don't forget that whenever we are using MnO2 as oxidizing agent, observe that solvent is acetone or CCl4. And similar to that reaction, oxidation with halogens. In a haloform reaction or iodoform reaction, we learned that ethyl alcohol upon reaction with a halogen, we are getting acetaldehyde. Their halogen or chlorine acts as generally oxidizing agent. So how halogen acts as oxidizing agent, let us see here. I am going to consider bromine molecule. This one upon reaction with the primary alcohol. Means if you consider ethyl alcohol, here R is nothing but CH3, CH2OH, just like that. Here what happened? Br bond is polarizable, and this one Br is going to take away electrons, and this bromine is obviously acquires partial positive charge, and this one acquires partial negative charge. Upon this partially positively charged bromine, CH bond hydrogen going to shift, and this one comes out as HBr. And in order to accommodate that, oxygen lone pair will be participated in resonance. Hence we are getting RCH, double bond OH plus, because oxygen on the red electron pair and OH plus. After losing this H plus, we are getting aldehyde. That means alcohols, primary alcohols particularly converts into aldehydes upon reaction with halogen. This is clear, but here can we use chlorine or any halogen acts as good oxidizing agent for oxidation of primary alcohols into aldehydes? No, because after formation of that aldehydes, alpha carbon means with respect to this C double bond or adjacent carbon, what we call alpha carbon, that alpha carbon containing hydrogens also can be replaced by halogen atoms. I am repeating, here reaction will not be stopped after formation of aldehyde, and further reaction continues. How it continues? And they can replace that. CH bonds, with CH bonds, alpha CH bonds into alpha haloaldehydes. That means displacement reactions also proceeds. That's why this method is not suggestible for oxidation of primary alcohols into aldehydes. Sir, these halogen atoms can only oxidize primary alcohols into aldehydes? No, they can also oxidize secondary alcohols into ketones. So primary alcohols into aldehydes, secondary alcohols into ketones, that happens. And don't forget that here further alpha halogenation also possible. That's why this one is not a suitable method for oxidation. Let us see. FeSO4 and hydrogen peroxide. Hydrogen peroxide is good oxidizing agent. Hydrogen peroxide is good oxidizing agent. Hydrogen peroxide it itself can oxidize alcohols into aldehydes, but aldehydes also further oxidize into carboxylic acids. Aldehydes also further oxidize into carboxylic acids. But with Fenton's reagent, FeSO4 and H2O, it is called Fenton's reagent. Fenton's reagent is the reagent which is used to find out enols. Enols means carbon-carbon double bonds, carbon-carbon double bond and double bond carbon containing OH. These type of groups we can identify, we can recognize. Means in order to test enols, we can use this reagent, Fenton's reagent we can use. Okay, don't forget that. Fenton's reagent, testing reagent for enols, means for phenols also we can use this reagent. Phenols identification test, we can use Fenton's reagent. So how the reaction mechanism proceeds, that we will discuss in phenols. But just remember that this one is testing reagent for enols. Now here how this mechanism proceeds. Hydrogen peroxide is oxidizing agent and Fe plus 2 it readily oxidizes into Fe plus 3. Fe plus 2 readily oxidizes into Fe plus 3. When we are using ferrous sulfate and hydrogen peroxide and when these two are involving in reaction, hydrogen peroxide, just assume that it undergoes homolytic equation as 2 OH groups, HO and OH. Upon homolysis 2 OH radicals you are getting, and of which one radical is going to take electron, is going to accept electron from Fe plus 2. Further Fe plus 2 converts into Fe plus 3, and OH minus which accepts electron from Fe plus 2 that converts into OH minus, still it consists one OH radical. Remember that this OH radical is going to take part in the reaction. See, this one upon reaction with alcohols, whether it is a primary alcohol or secondary alcohol, whatever it may be, then what happens here? This OH abstracts one of the hydrogen from CH bond, CH group, resultant we are getting like this radical. This radical, whenever free radical formation takes place or whenever the reaction proceeds via formation of free radical, this is out of our control, and for that there is no activation energies required. Hence, whenever free radical mechanism, you may get different products, of which major product is dimerization product. Resultant dimerization, you are getting dimerized product. So this is a diol. And formation of diol, in previous session also we learned, like with osmium tetroxide KMnO4, there also diol formation you mentioned, and there particularly we learned that the syn diol means both the OH groups are going to attach from same side with respect to double bond. That we learned. So can we say like this, here there is no double bond, that's why there is no syn such words applicable here, point to be noted. And second one, in case of KMnO4 and osmium tetroxide, whatever the diols we are getting, the diols are vicinal diols, means both the OH groups attached to adjacent carbon atoms. Here we cannot say like that. Always we are getting like vicinal diols, geminal diols, no geminal diols, no doubt in that one. Vicinal diols we cannot say. That is only diol, two OH groups, but they need not to be attached to adjacent carbon atoms. They may attach anywhere, and hence we are getting here product a diol. So with the Fenton's reagent, we are getting alcohols to diol. We are getting this also oxidation. And let us see mechanism of chromic acid. How this one converts alcohols into carbonyl compounds, means primary alcohols into aldehydes and secondary alcohols into ketones. How that mechanism proceeds, let us see. H2CrO4 chromic acid, this one also we can say CrO3 in dilute H2SO4, there also you are getting H2CrO4. In H2CrO4, chromium is +6 oxidation state. So chromic acid basically orange color. Chromic acid salt is chromate. Chromate upon dimerization in acid medium it converts into dichromate, that is yellow color. Orange color chromate converts into yellow color dichromate in acid medium. In acid medium dichromate form exists, in base medium chromate form exists. Okay, remember that. So orange color, this orange color chromic acid converts into Cr plus 3. Earlier it was Cr plus 6. Now it converts into, means after oxidation, because of it acts as oxidizing agent. Because of it itself acts as oxidizing agent, it has to reduce itself. That's why its oxidation number is going to reduce from plus 6 to plus 3. So Cr plus 3 is green color. Also we can say bluish green. Green or bluish green. So orange color converts into green color. It indicates that yes, oxidation reaction is completed. Means with our naked eye we can identify that yes, oxidation reaction is completed simply by changing the color. So remember that chromic acid, this is orange color, and upon acts as oxidizing agent, it has to reduce itself to Cr plus 3, which is green color. Now chromic acid in water, it behaves as acid, and what happens? It donates proton to water molecule. That means in water it itself acts as acid, and water here acts as base. It accepts a proton and it converts into H3O plus and HCrO4 minus. Now this HCrO4 minus is going to take part in oxidation of alcohols. Let us see here RCH2OH. I am going to consider primary alcohol. In primary alcohol, oxygen, this one possesses two lone pairs, and in HCrO4 minus, I am going to write the structure Cr double bond O minus and OH. Now this oxygen is coordinated with the central chromium in order to facilitate that this double bond electrons are shifted towards oxygen, and this O minus is going to accept proton from solvent. I am repeating once again. I used to consider first primary alcohol RCH2OH, in which oxygen possesses two lone pairs. Now in alcohol, oxygen containing lone pair is coordinated with central chromium in HCrO3 minus, and in order to facilitate that, means there Cr plus 6 acts as electron pair acceptor, means Lewis acid, and alcohol acts as Lewis base. And in order to accommodate that pair of electron provided by oxygen, these pi electrons are shifted towards more electronegative oxygen. And whenever that happens, oxygen gets, this chromium containing oxygen acquires negative charge. That negatively charged oxygen, because of this reaction mechanism performed in acid medium chromic acid, already chromic acid gives H plus to water, and that solution is proton rich, H3O plus exists. This O minus takes that H plus. See, means water molecule is going to transfer. Water molecule acts as mediator. Water molecule really here acts as solvent. So it accepts a proton and again it will give proton. See, here it is donating proton. Earlier it accepts proton from H2CrO4. Now this one is giving back proton to O minus. Resultant what happened? RCH2. This oxygen is coordinated with chromium. And earlier it possesses one hydrogen like this. Yes, this hydrogen. Oxygen coordinated with chromium, hydrogen and carbon means 3 valency. Resultant oxygen is going to bear positive charge. When oxygen is going to bear positive charge there, here Cr, this double bond converts into OH, earlier it OH, two OH groups, and this O minus and double bond O structure as such. After getting the structure, further what happened if you observe clearly, H3O plus again is giving H plus to this one. Here H3O plus is donating proton to this OH group. And here water accepting H plus from the same substrate. That means from O plus, there water molecule is going to accept. A proton. Water molecule is going to accept a proton. Whereas here H3O plus giving a proton to OH. Resultant, this OH converts into OH2 plus, and this OH group converts into normal oxygen. Means COCr, and this O minus just giving back electron to this one. There will be a formation of Cr double bond O in between this chromium and oxygen. Hence we are getting RCH2O Cr double bond OH. After formation of this chromic ester, this is what we call chromic ester. So chromic acid mechanism via formation of chromic ester. and there KMnO4 OSO4 oxidation via 5-membered cyclic transition state. There we are getting vicinal dipole. Here you are not getting any vicinal dipole. Here also we can say the structure Cr double bond O minus we can show like that. But this mechanism is completely different from KMnO4 mechanism. So here after hydrolysis, here what happened here? This CH bond is going to turn towards oxygen and OCr bond will be shifted towards chromium in order to facilitate that pi electrons are shifted towards oxygen. Finally, we are getting aldehyde and HCrO3 minus. So, in this case, if you observe H2CrO4, it acts as oxidizing agent and plus 6 converts into plus 4. Right now, it is plus 4. Here Cr minus 6 plus 1 is equal to minus 1. So here it converts into minus 5 plus 4. So chromium plus 4 it comes here. And further reaction you are getting Cr plus 3. Cr plus 3 which is in green color. Here mechanism with PCC. Chromic acid mechanism will learn. Now PCC and Swan's oxidation, in these two reactions, how oxidation mechanism proceeds, let us see. PCC, pyridinium chlorochromate, means CrO3, pyridine and HCl. As we mentioned earlier, here pyridine is not going to coordinate with chromium of chromium oxide. How reaction proceeds? Pyridine is base, it reacts with HCl and converts into pyridinium chloride. This pyridinium chloride Cl minus coordinate with the chromium of CrO3 and we are getting reagent. That reagent is nothing but ionic compound, means salt. Cr, here double bond O minus Cl and pyridinium ion. Now in which pyridinium ion is a spectator, it is not going to take part in the reaction. And which one is going to take part in the reaction? Here CrO3, Cl minus. This one is going to take part in the reaction. Let us see. I used to consider primary alcohol as primary alcohol can be oxidized to aldehyde, secondary alcohols can be converted to ketones. Here I am going to consider primary alcohol. Primary alcohol oxygen possess two lone pairs of which one of the lone pair will be coordinated to chromium. In order to facilitate that, Cr double bond O pi electrons are shifted towards more electronegative oxygen. Resultant oxygen chromium bond formation takes place. Resultant oxygen is going to bear positive charge. And already O minus is there because of pi electrons are shifted towards this oxygen. This oxygen also going to bear 2 negative charge. Here total 2 units negative charge and 2 units positive charge is there. One is with nitrogen positive charge, another one is oxygen positive charge. Next case, this OH bond is going to break. In order to compensate the positive charge, this H plus will be taken by O minus. That means proton transfer takes place from one oxygen to another oxygen. And from that means whenever proton transfer takes place, still consists one negative charge and one positive charge. And whenever oxygen containing negative charge tend back, and Cl has to come out as Cl minus, and pyridinium chloride salt comes out, and you are getting again chromic ester. There also chromic ester formation, here also chromic ester formation, but the formation of chromic ester mechanism is different. And here after formation of chromic ester, Cl minus has to abstract H plus from this oxygen containing carbon, and that negative charge will tend towards oxygen, and OCr bond is going to break, and that Cr that sigma bond electrons are shifted towards chromium. In order to facilitate that, pi electrons are shifted towards oxygen. Hence we are getting aldehyde and H2CrO3 and pyridinium chloride. So in mechanism with PCC, direct coordination with nitrogen is not there. It prefers to accept that H plus from HCl, and rather than it behaves as a nucleophile. And after formation of pyridinium chloride, it reacts with CrO3 and it forms a salt, and in that salt anionic path is going to take part in the reaction. And finally we are getting chromic ester. After formation of chromic ester, Cl minus abstracts H plus from the carbon, which extend to oxygen, alcoholic oxygen, and negative charge will be shifted towards oxygen, and OCr bond is going to shift towards chromium, and CrO pi electrons are shifted towards oxygen. Means whenever the CrO pi electrons are shifted and chromium electronegativity increases, whenever chromium electronegativity increases, it pulls OCr bond electron towards itself, and immediately the CH bond electron shifted towards oxygen. So reverse pattern, if you think, you will get correct phenomena. or else if you think like that Cl minus how it abstract proton, if you consider like that, you are getting complete somewhat confusion. Means how Cl minus abstract is plus. But if you think like this, whenever Cl double bond to double bond O is there, and it pulls electrons, pi electrons towards itself, here also it pulls towards itself, resultant chromium acquires more and more positive charge. Whenever more and more positive charge developed upon chromium, its electronegativity increases. Whenever chromium electronegativity increases, obviously it pulls electron from oxygen, and whenever it pulls electron from oxygen, oxygen turns to electron deficient, then immediately it pulls electron from adjacent carbon containing hydrogen. So that mechanism happens here. We are getting from primary alcohols to aldehyde, from secondary alcohols to ketones. And Swan's oxidation, in Swan's oxidation also primary alcohol converts into aldehyde, secondary alcohol converts into ketones we learned. But then in there we are using DMSO, dimethyl sulfoxide, and oxalyl chloride, just like acid chloride, oxalic acid chloride, oxalyl chloride. And triethylamine is a base, that means nitrogenous base. As I mentioned that we have to use weak base, we are not supposed to use any strong base. See what happened in reaction. Let us see first onwards. Dimethyl sulfoxide S double bond O CH3 in which S double bond O is there. This S double bond O pi electrons are shifted towards more electronegative oxygen, and oxygen already bears two lone pairs and it ready to donate its lone pair of electron to any electron deficient here. Oxalyl chloride C double bond O Cl is there. When pi electrons are shifted towards oxygen, carbon acquires positive charge. Towards that positive charge, dimethyl sulfoxide O minus has to come and attack. Then there will be new bond formation between O oxygen of dimethyl sulfoxide and carbon of oxalyl chloride. Resultant you are getting CH3 S. Because of pi electrons shifted towards oxygen, S is going to bear positive charge, and there is a new bond formation between oxygen and carbon, and O minus remaining part C double bond with Cl and Cl as such. And whenever O minus stands means upon reversal of the charge, negative charge, Cl has to leave, and this Cl comes out as Cl minus. Then we are getting product methyl S plus O, C double bond O, C double bond O Cl. The one Cl minus which comes out, there, that only further next step acts as nucleophile. It prefers to attack upon this positively charged sulfur. It prefers to attack upon positively charged sulfur, and these electrons are shifted towards this carbon, and this Cl has to come out. So if here the nucleophilic attack takes place, SO bond breaking, CC bond breaking, CCl bond breaking, resultant we are getting two methyl groups of sulfur containing chloride. Again it bears positive charge, carbon monoxide, carbon dioxide. So from oxalyl chloride, both carbon salts to come out as carbon monoxide gas and carbon dioxide gas. Now we are getting an electrophile. So ultimately, so far what happened here? Production of electrophile, formation of electrophile only happens. So there is no real mechanism so far started. Right now, real hero means alcohol is going to start reaction with that electrophile. Basically, alcohols are nothing but there is 6 positive charge because of oxygen base, 2 lone pairs. Then it donates lone pair of electron to positive charge of sulfur. Then there will be new bond formation between oxygen and sulfur. We are getting RCH. If we consider secondary alcohol, if we consider primary alcohol, then primary alcohol only going to take part. So this oxygen sulfur bond formation, and oxygen is going to be a positive charge. Whenever this OH bond electrons are shifted towards oxygen, simultaneously HCl minus has to come out. This H plus and Cl comes out as HCl. And RCHOS double bond SCH3CH3. When we are using triethylamine, this triethylamine abstract proton from this carbon, from this methyl group containing carbon, we are getting CH2 minus, and CH2 minus when abstracts proton from here, and this CH bond electrons are shifted towards carbon oxygen, and OS bond is going to break. Resultant we are getting ketone. In case of primary alcohols, we are getting aldehydes. In case of secondary alcohols, we are getting ketones. Let us consider oxidation of secondary alcohols. So far we discussed primary alcohols. So primary alcohols upon oxidation we are getting aldehydes. And with a few reagents like acidified alkaline KMnO4 or acidified potassium dichromate, formed aldehydes also oxidize into carboxylic acids. But With the secondary alcohols readily convert into ketones with the same number of carbon atoms. In case of primary alcohol oxidized to aldehyde, aldehyde to acid, there is no change in number of carbon atoms. What number of carbon atoms are present in alcohol? Same number of carbon atoms are present in aldehyde and same number of carbon atoms are present in carboxylic acid. But in case of secondary alcohols, the number of carbon atoms present in secondary alcohols and ketones are same. Means RCH, OH, CH. This one is secondary alcohol which are upon oxidation, whether it is a mild oxidizing agent or strong oxidizing agent, or until formation of C double bond means ketone, here reaction fast, and after formation of ketone further oxidation to carboxylic acid, we need to provide heat energy because carbon-carbon bond breaking has to take place. In order to break that carbon-carbon bond, we have to provide heat energy, otherwise reaction will be stopped here. And in case of primary alcohol, if you want to stop after formation of aldehyde, you have to use better only mild oxidizing agent rather strong oxidizing agents. If you are using strong oxidizing agent, then what happens? They converts into formed aldehyde converts into carboxylic acid. But in this case, after formation of ketone, whether the oxidizing agent is strong or weak, what happens? Heat energy must. If it is weak oxidizing agent, further reaction, oxidation do not take place. If it is strong oxidizing agent, it will take some time to break that carbon-carbon bond. Meanwhile, you cannot separate that formed ketone. So, here ketone also further oxidation, we are getting carboxylic acid. Compared to aldehyde, oxidation of ketones are somewhat difficult because in case of oxidation of aldehyde, there is no carbon-carbon bond breaking happens. In case of ketones, carbon-carbon bond breaking takes place. And difficult to oxidize ketones gives carboxylic acid with a strong oxidizing agent like acidified potassium bichromate and heat. Let us see, I am going to consider CH3, CH, OH, CH3. This one upon oxidation, whether strong or mild, it converts into ketone means acetone. In case of acetone, C double bond O group attached to two methyl groups. Since both C double bond O group is attached to two methyl groups, here both alkyl groups are same. This one upon further oxidation, which bond is going to break? That is meaningless. Either of the bond has to break. And we are getting CH3COOH, CH3 C double bond OH means two carbons containing carboxylic acid, and remaining part is one carbon containing carboxylic acid. Remaining part is one carbon containing carboxylic acid. That means total 3 carbons containing alcohol we used to consider. 3 carbons containing alcohol we used to consider. Which upon oxidation you are getting 3 carbon containing ketone. 3 carbon containing ketone upon bond breaking we are getting 2 carbon containing carboxylic acid and 1 carbon containing carboxylic acid. This 1 carbon containing carboxylic acid converts into CO2 and H2O. It oxidizes further in CO2 into H2O. Fine, sir. If we consider alcohol, secondary alcohol, in which OH containing carbon is attached to one methyl and one ethyl. One methyl and one ethyl. This one upon oxidation, we are getting CH3, C double bond O, C2H5. This one is ethyl methyl ketone. This ethyl methyl ketone upon oxidation, what happens? Ethyl methyl ketone upon oxidation, here one is 2 carbon containing alkyl group and another one is 1 carbon containing alkyl group. So which bond has to break? So suppose if bond breaking here takes place, then 1 carbon containing carboxylic acid, 3 carbon containing carboxylic acid, 2 products you are getting. If bond breaking here takes place, 2 carbon containing carboxylic acid and 2 carbon containing carboxylic acid means both are 2 carbon containing carboxylic acid. So where bond has to break down? That one given by Popoff's rule. Here Popoff's rule is in case of unsymmetrical ketone oxidation. In case of oxidation of unsymmetrical ketones, C double bond O group goes along with small alkyl group. In other words, C double bond O group always comes to the alkyl group which consists less number of carbon atoms. Here one alkyl group consists 2 carbons, one alkyl group consists only 1 carbon. Then C double bond O group goes to 1 carbon containing alkyl group. So here bond cleavage takes place. Resultant these 2 carbon containing carboxylic acid, these 2 carbon containing carboxylic acid we are getting. This one is Popoff's rule. So this one is regarding secondary alcohols to ketones, and ketones when oxidized further into carboxylic acid, you notice that less number of carbon atoms. So whereas here alcohols to ketones, there is no change in number of carbon atoms. But when ketones oxidize to carboxylic acid, there will be less number of carbon atom containing carboxylic acid you are getting. Tertiary alcohols resistant towards oxidation, and we learned in previous sessions under the name of dehydrogenation, catalytic dehydrogenation by heating copper and 300 degrees Celsius or 573 Kelvin. So there, instead of oxidation, instead of dehydrogenation, dehydration takes place, we learn. Similar mechanism here also. Tertiary alcohols do not undergo oxidation because of, in case of tertiary alcohols, there is no CH bond here. OH containing carbon is not attached to any hydrogen. All three are carbon atoms. That's why upon oxidation with strong oxidizing agent like concentrated HNO3, here what happened? Carbon-carbon bond breaking, not possible here. That's why initially dehydration takes place. So OH and H2O eliminates and you are getting isobutene. Isobutene. This isobutene undergoes oxidation because of carbon-carbon double bond is there. This is electron rich. Nascent oxygen has to come and attach here. So here two OH groups, further bond breaking, again two OH groups. This one converts into ketone, acetone, and this one converts into formaldehyde. Formaldehyde further oxidized to formic acid. Formic acid further oxidized to carbon dioxide. Because of strong oxidizing agent, you are getting ketone and carbon dioxide. And if this ketone also further oxidizes, then this bond breaking takes place again. For two carbon containing carboxylic acid, carbon dioxide, and H2O. And here haloform reaction already we learned in case of chloroform. Here ethyl alcohol with bleaching powder also gives haloform reaction. That I am not going to mention, but you need to recollect once that haloform reaction how ethyl alcohol is going to react with bleaching powder. These are reactions, oxidation reactions of alcohols.